Hi everybody. So part A, explain Newton's method in the context of this equation, this problem that we've been working with. It says use an initial guess of 2, 2 and explicitly write the first linearized system, though you need not solve it. Okay, so first thing I'll do is I'll do a formula. I'll calculate the gradient of g. So we're trying to minimize a function g, and so we want to find where the gradient is 0, and those are the critical points. So first we'll just compute the gradient. Okay, so the gradient sends xy to, let's see, I need to take partial x of all this stuff, and that's the first component of the output, and then partial y of all this stuff, and that'll be the second component. Okay, so I can do that. So first partial x, I get 8x to the third, what is it, plus 2y squared minus 2x, and 0, 0, 0. Okay, second component is partial y. This gives a 0. Here we get a 4y to the third. Here we get a 4xy. And 0, and a minus 2/3 y. And a 0. Okay, so there's the gradient. And now I have to explain Newton's method in the context of this example. So in the initial guess, they said it should be 2, 2. Okay, so Newton's method begins by guessing. By guessing and checking and check. Okay, so what do? We just plug in, let p equals 2, 2. Then the gradient of g at p, well, I have to plug in 2. So I get okay, and then this one becomes 2 to the third, 4 times 2 times 2, and minus 2/3 times 2. Okay, so what's this? So if it's 0, 0, then we're great. We found the critical point. But it's probably not going to be 0, 0, because it's a guess. 8 times 8 is 64, plus 2 times 4 is 8, minus 4. Here we'll get 4 times 8 is 32, plus 16, minus 4/3. Okay, yeah, this is looking like it's not going to be 0, 0. Okay, so this is 68, 48, minus 4/3, whatever that is. Okay, so I guess we could write that as like 46.6, or I'll just leave it at that. So this is not 0, 0. So this is not a critical point. Well, we just guessed the point, so okay. So let's linearize. So this is the next step that Newton's method does. It takes the derivative. Take the derivative. Okay, and now we'll see why we're doing that in a moment, but first we can just take the derivative. So the derivative of the map, gradient of g, at the point P, well, that is a map with the same input and output. We're taking the derivative, not of g. We are not taking the derivative of g. This is weird. We're taking the derivative of the gradient. Okay, we can do that. It sends v1, v2 to something, v1 times, and now this is the first column of the Jacobian, so I can take the partial with respect to x, and I get 3 times 8 is 24, x squared, and minus 2. And then the partial with respect to y is for y, okay? Plus v2 times, okay, now I look at this component, I take partial with respect to x, and I get 4y, that's it. And then I take partial with respect to y, and I get 12y squared plus 4x minus 2/3. Okay, but, you know, at p equals 2, 2, our guess, this becomes what? Okay, derivative grad g at p. It'll send v1, v2 to v1 times, okay, now I plug in 2, 2. So this becomes 24 times 2 squared minus 2, and this becomes 8. And then v2 is, okay, now this becomes an 8. I plug in at 2, 2, and I get 12 times 2 squared plus 4 times 2 minus 2/3. Okay, so what is this? This is v1 times, okay, 4 times 24, 80, 96, minus 2 is 94. And then what's this? Well, okay, 8, and then what's this stuff? 4 times 12 is 48, plus 8 is 56, minus 2/3 is 55.3333333, etc. Okay, so now why would Newton do this? Or why would Newton's method do this? Newton's method was actually discovered by many, many people because it's just linearizing. We want to move from our guess to, you know, our guess was, what was it? It was called P, to a new point at P plus V. And so look at linear approximation. And so now I need a formula, the linear approximation formula. Normally we would write f of p plus v is roughly equal to f of p plus the derivative of f at p applied to v. Okay, but our map here is actually, we want the gradient to be 0. And so actually instead of f, it's the gradient of g at p plus v is basically equal to the gradient of g at p plus the derivative. And so now we have the derivative. What is it? Well, here, I'll just write it out. Derivative of the gradient at the point P on vector V. Now, I'll put in words. We want this to be 0. Right? We checked. The gradient at P was something very specific. Here it was 6846.6. So this was 6846.6. That was not 0. We would rather it be 0, right? We would rather this be 0. So this piece we'd want to be 0. And here's the gradient at our guess. And then here is the derivative at our guess point. So let me just plug in. 94, 8 plus 8, 55.3. And then hold on a second. We can solve for v. So I'm going to put that in red. We can solve this linear system of equations for v. V is a, it's a movement in our input space, v1, v2. And that'll tell us how to take our lousy guess, which had which was not a critical point. The gradient was not the zero vector. And we're going to move so that maybe the gradient will become the zero vector at our new point, p plus v. So we can solve this linear equation, so this system of linear equations for v, and get a better guess, namely, what is it? P plus v. And just to show what these linear equations are, I look at this thing and I'm going to read off the equation. 94v1 plus 8v2 equals negative 68. I just looked at this top row and I moved the 68 to the other side. Now I look at the bottom row and I get, 8v1 plus 55.3 times v2 equals negative 46.6. And this we can solve. So now the question specifically said, write the first linearized system, though you need not solve it. Okay, so we're done. We used the initial guess point, we linearized the system and wrote it down, and we're not going to solve it, but then what it would do is it would produce this step. So here's the point P equals 2 comma 2. So you see here's the 2 and there's the 2. And this is V. V. So Newton's method, find V that is closer to a critical point. And so this point right here, or maybe I'll label it in a different color right there. This is P plus V. Okay? How do we find this movement V? Well, we wanted the gradient to be 0. So we just looked at this linearization formula. We wanted the gradient to be 0. We guessed, and it wasn't 0, it was this. And so we're just going to move in order to make it 0. And it won't exactly work because this formula is only linear approximation. But this is the idea. And then we just repeat. Now our new guess is P plus V, and we repeat. And we would find another step. And we'd step again, and we'd just keep repeating this process and eventually get to this critical point right there, it looks like. And so this is Newton's method. Add any relevant labels to the picture below. Yeah, I did. There's our guess. Here's V that we're going to find, and here's P plus V. Okay, so this is the solution I wrote down. And you can see very, very important is the order of things here. How I'm sort of explaining as I go through the calculation. Of course, there's formulas I need to compute the gradient. I need to compute it at the point where we guessed. Then I sort of say what we're going to do next. So I compute the derivative. I plug it in at that point. And now here's very crucial. I'm saying what we're going to do is we're going to move to a new point. And this formula, as always, just keeps coming up everywhere we go. Linear approximation. And so, this part right here is very crucial. We want that to be 0. That's why Newton's method will get us there eventually. And so we solved a linear system of equations. And I wrote them down specifically right there. Okay. Before I go, I'll just say that Newton's method will solve any system of equations of any size sometimes. We're going to just keep taking steps, and we hope that it converges to one of the solutions. Here, there's actually 7 solutions to our critical point equations, the gradient being 0. And, if we start at 2, 2, we're going to find one of those solutions. So then we could choose a new guess point, and we could start there, and we'll start moving around, and maybe we'll find a second solution. And we could take another guess and see if we can get a third solution. And this will work in any dimension, because look at what we're doing. We solve a linear system of equations. We can solve those in more variables. And we're moving by a vector, P plus V. And vector addition, we know how to do in any dimension. You just add each of the components of the vectors. Okay, see you next time, everybody.